allow you to kind of roughly estimate what these parameters are. And so, you know, the boson energy we're extracting out is quite small. So it's sort of on the range of, you know, let's say about 15 to 20 millielectron volts. And so, you know, for the 214, we were a little bit unsure as to whether or not these were, let's say, dressed by spin or lattice excitation. But we know that in 327, there's a large spin gap, about 90 millivolts. So, you know, that's much, much higher than the sort of boson energy that we're extracting out. So my guess is that it's likely due to some kind of lattice, lattice mode. Now, whether or not these things are, you know, relevant for some ostensible high DC superconductivity in iridates, I really don't know the answer to that question. But again, I think it's just very striking that the parent insulators of both the cuprates and the iridates seem to show a lot of, you know, remarkable similarities beyond just sort of the superficial looking at sort of the magnetic and electronic. So even sort of in the details of, you know, the single particle excitation spectrum, they look really very similar. Okay, so I'm going to talk now about strontium iridium 3. Change gears a little bit. This one is semi-metallic. It's not, it's not an insulator. And, so there's some questions as to, okay, well, when you're going, progressively from 2D to 3D, why does it become metallic? It's just a simple sort of bandwidth sort of picture. Okay, you've got more neighbors connected, so, your hoppings are, your hopping such that, U over T is going to be smaller. So this, was first found by Taiwan No's group. So they did, optical measurements. So you can see the 214, 3 are both insulating. There's a small gap here, and then here for the 113, using this large Drude peak. And so, one, I think quite intuitive picture would just be, okay, as you're going from, more 2D to 3D, you have more connectivity, so maybe it's just a bandwidth issue. And so this material has a lot of other, there's a lot of other potential interest in the strontium iridium 03. So AMC's group has done a lot of work suggesting that this material may have interesting possible topological character. So there may be line nodes in the bulk, possibly some kind of topological semi-metal kind of state. And also Young's group has also worked on this as well. And then there's been a lot of interesting work on superlattices or bilayers of this. So there's been proposals from Okamoto and Nagosa sensei's groups, and of course this is a picture from Hide Takagi's group where they've been making 111 and 001 strontium iridate, strontium titanate. So we kind of wanted to understand this building block a little bit better, because it might be sort of an interesting material for engineering topological phases kind of superlattice. And that's sort of the original intent of our work, was to try to make kind of superlattice, but we're starting kind of just with the actual building block itself. So this particular compound, strontium iridium 3 and perovskite, does not is metastable in bulk. So if you try to make a bulk crystal of this, it forms, I believe, in a hexagonal structure. And so, but you can epitaxically stabilize it. So this was the work first done by Taiwan No, and also by my former postdoc Yu Feng. So Yu Feng was able to grow strontium iridium 03 by MBE on LSAT substrates. And so, so you get quite nice thin films. So here's a TEM image. You can see it's nicely coherent to substrate. And, you see a large temperature-dependent Hall coefficient, which suggests, okay, maybe it's a semi-metal with electrons and holes. There's probably a couple different bands and holes here. Okay, so I'm going to like to compare this to first with the 214. So this is photo emission that we did on strontium-2 iridium 04. These were thin films that we grew, but they're very similar to the single crystals. And so, basically, of course, there's no intensity right at the Fermi level, but if I look kind of, 200 millivolts below, you see the 1/2 and 3/2 bands, so sort of broad feature. And the 1/2 and 3/2 bands are actually not particularly narrow. Okay, so if you actually track their dispersion, they're sort of on the range of 800 millielectron volts, sort of, on the order of a volt wide. So they're quite wide. And so we were quite surprised when we looked at strontium iridium 03. So that's down here, and this is the Fermi surface. And so you see both these little electron pockets here and these large hole pockets of pi zero. This is a 2D slice in a three-dimensional Brillouin zone, but we're just concentrating with this one 2D slice. And the thing that was quite surprising to us is that you see these individual bands. So first of all, you get these very sharp quasi-particle peaks. So they don't have this sort of polaronic feature. Of course, a metal, so there's a lot better screening than you would have in the insulator. But these peaks are much sharper. And also these individual bands are much, much narrower than they are in the 214. And you can see that right here. This one band here. You see a lot of these little bands that are sort of moving in and out. And so if we extract out and see the peak positions that we get from these image plots, you get something like this. The pink is the 214, right? So you can see these bands, the 1/2 and 3/2 states. And then the strontium iridium 03 is a blue dot, right? So you can see first of all, a lot more bands, and they're individually relatively narrow. Okay? So we are a little bit surprised by that. And this was the work of Yifeng. So we started talking with Craig Feeney, and actually you heard in Feng's talk, basically the importance of octahedral rotation. So strontium iridium 03 is not cubic, okay? So it has octahedral rotations in all three directions. And so we said, okay, well, what is the relevance of the octahedral rotations? So in 214, if you have no rotations and you put rotations, you get zone folding, but beyond that, it actually doesn't seem to be a really substantial effect to the electronic structure. And then so Chung, who was Craig's postdoc, did some calculations with the 113. So these are all with spin orbit, but we turned U off just because we weren't really sure what kind of U to use on strontium iridate, just to make a fair comparison. These are both with no U. And so this is strontium iridium 03 in the cubic, idealized cubic structure. And then when you add all the rotations in, you can see there's a lot of these little bands that are quite narrow. And so there's a much more complicated band structure, which is partially due to zone folding. Another thing that's quite interesting is that the color coding, red is more 1/2, and blue is more 3/2. And you can see actually, unfortunately, white is not a good color, but it turns out that a lot of the bands that are near the Fermi level have very mixed character in the strontium iridium. So it's not really here, sort of talking about 1/2 and 3/2 states. It makes pretty good sense. Here, some of the bands have highly mixed J character. And that's from Chung's calculations. One important thing we needed to do was to actually verify that our films indeed had those rotations. That's relatively difficult to do in bulk and thin films. It's a little bit more challenging, so we did some synchrotron X-ray diffraction at Chess at Cornell, and some TEM and LEAD as well. And so you can actually see all the different rotations in our films. So our films are under some compression, so it's not entirely clear if they will have the same rotation pattern as in bulk, but we do see all these rotations. So that calculation, I think, is rather valid. So I'll sort of close the discussion on strontium iridate by also mentioning there are some interesting features in the electronic structure. So akin to sort of what Young's group has predicted, we do see something that looks sort of like, kind of like a Dirac-like cone, or it's a very light electron mass cone. So it may be relevant to this line node predicted. We need to do a sort of a full photon energy dependence to really see if that is indeed the case. But it seems consistent with some of the band structure calculations that her group has done. And actually, in addition, we have these very, very massive full bands. So if you look at the mass here and the mass here, they're different almost by a factor of 30 in the effective masses. And so that kind of, may nicely explain why we have this very temperature-dependent Hall coefficient. Very heavy full bands and very light electron bands. Again, this feature here is, I think, it's the same case point that they predicted this feature here in their band structure. So one last thing that we think might be interesting to do with strontium iridate 113 is that, so as I mentioned, it's these octahedral rotations that we suspect are really responsible for narrowing the bands and making the band structure sort of very complex. So the idea, so what if you could somehow unrotate the octahedra? You could sort of make it in the idealized cubic structure. And that is indeed possible. So there's actually another metastable state, barium iridium-03, and that one has 180-degree bonds. People have been able to make that under high pressure, and that one is quite metallic. And our calculations of basically that kind of structure is, this is plotted in the same energy scale, right? So you see these very narrow bands here, and these are the same bands. They're basically, the mobilities are like more than 10 times higher because the bandwidths are so much larger. So it'd be interesting to test this prediction by trying to make, let's say, the high symmetry structure to see if really this is indeed the case. Okay, I have a couple minutes left, so I just want to very briefly show some preliminary stuff we've been doing on some heterostructures, and actually moving away from the Ruddleson-Popper phases. And this is something that my postdoc Jason, who's here in the audience, he was a graduate student here at Santa Barbara, has done some beautiful work working on the rutile structure of iridium-02. And it, at face value, is quite similar to iridium-4+, just like the Ruddleson-Poppers, and it's iridium inside octahedral cages. But instead of just having the corner shared octahedra that you have in the perovskite type structures, these have both corner and edge shared octahedras. So there's sort of a higher level of connectivity in these rutile structures than in the perovskites. And so we were curious